Welcome back to the next video, everybody. Today is part 2 of my series of talks generalizing discussions we had in previous videos. Today we're going to focus on generalizing Hecke algebras to look at them over various other rings other than just the complex numbers and the integers. Okay, so how about over Q and Z? Over Q, one basic fact that you want to be aware of is that T sub Q, which remember is T sub Z tensor Q, is the direct sum over this bracket F notation of K sub F. Remember, K sub F is the number field associated to a new form F. And what is this sum actually over? What does this bracket of F mean? It's just the sum over the orbits bracket F under the Galois action on new forms by the absolute Galois group of Q, which we discussed in a previous video. Okay, in fact, in a very recent video. Okay, you can also see that TQ acts naturally on lambda tensor Q, where lambda is the first integral homology of the modular curve X gamma. And of course, lambda tensor Q is just the first rational homology of X gamma as well. Why is that true? Well, we know it acts on the Jacobian. We know TZ acts on the Jacobian, right? Well, the Jacobian is just dual of space of holomorphic differentials mod first integral homology. So definitely TZ acts on lambda for sure, or else it has no chance at acting on the Jacobian. And then tensoring up to Q gives you the statement that I gave you here. Okay, and you can also check that lambda tensor Q is free of rank 2 over TQ. In other words, it's a rank 2 TQ module. Okay. All right. The thing is, I just want to say one thing about what happens over Z. Over Z, things aren't so nice. It actually isn't the case that lambda is free of rank 2 over TZ, despite the fact that when you tensor up to Q, you do get something free of rank 2 over TQ. Okay. Now, it's also natural to study Hecke rings or Hecke algebras over ZL and QL. And the reason of that is because we know we have a Hecke action on the Tate module, TL J gamma, which is the inverse limit over N of J gamma, the L to the N portion of J gamma, basically. Where J gamma is, remember, just the Jacobian associated to the congruent subgroup gamma. Okay, this action of the Hecke algebra is compatible with the Galois action, and it's this pair of actions and their compatibility which allows us to associate a two-dimensional Galois representation to modular forms, as we've talked about several times already. Okay, so long story short, yeah, we definitely want to consider Hecke algebras over ZL and QL. We have the following fundamental result. So let's let V be the L-adic Tate module of J gamma tensored up to QL. Then there's an isomorphism of TZL modules given by the L-adic Tate module of J gamma is isomorphic to its dual, which is the Hom or ZL of, it's just the ZL maps from TL J gamma to ZL. Okay, and so in particular, there's an isomorphism of TQL modules V with its dual V star, which is just ZL Homs from V to QL. Okay, so there's a nice isomorphism of TZL modules of V with its own dual. Okay, so this gives you a nice duality result that we'll play with later. All right, okay, the following result then allows me to regard TQL as a coefficient ring for a two-dimensional Galois representation from GQ to GL2 T sub QL. Okay, lemma, V is free of rank 2 over TQL. Okay, in other words, this, combined with the fact that I have compatibility of actions, gives me a two-dimensional Galois representation right here. Okay, and as a corollary, much like TC was Gorenstein, TQL is a Gorenstein QL algebra. In particular, both of these are free of rank 1 over TQL. So for a proof of this, or for proofs of really all of this, you can see Shimura's book on automorphic forms, chapter 3. Okay, and for summaries, you can see the Darman-Taylor notes, chapter 1. Let's bring Eichler-Shimura back now. Let's recall that for primes P that don't divide N, J gamma, the Jacobian, has good reduction mod P. And then Eichler-Shimura states that on J gamma slash FP, the reduction, TP is F plus diamond P F prime, where F prime is the transpose of F, given by the theory of dual isogenies. For primes P that don't divide NL, we can identify TL J gamma with the L-adic Tate module of the reduction. Now, this is not obvious. Okay, see Sayre Tate, good reduction of abelian varieties for a proof of this. And we can consider the Frobenius endomorphism F then on the free rank 2 TQL module given by V. Okay, so theorem, and this is sort of even a slightly more general result than we need to bring back and wrap up and add more detail to our discussion about Galois representations attached to new forms. If P doesn't divide NL and is prime, then the characteristic polynomial of Frobenius F on V is just x squared minus TPx plus diamond of P times P. Okay, so this is a more general statement than the one that I gave you way back in the day when we were going through the summary of the proof of Fermat's last theorem. This is basically saying, yeah, like the Hecke operators govern the trace of Frobenius, and the diamond operators govern the determinant or the constant term of the characteristic polynomial in some sense. Okay, this was a crucial property of the Galois representation attached to new forms that we went over way back in the day. So I'll give you just a quick proof of this. You basically just use Eichler-Schmidt twice. You know f prime f is P because f prime is essentially the dual isogeny of f, and f is a degree P map because it's the Pth Frobenius. So by Eichler-Schmidt, this is a quick exercise. F squared minus TPF plus diamond of PP equals 0. In other words, f does satisfy the characteristic polynomial. That's easy to check. So then to check that it's actually the characteristic polynomial of f on V, you just have to compute the trace of Frobenius. And we've essentially already done that. The proof mimics the proof we gave for the converse to modularity by using Eichler-Schmidt to conclude that twice the trace of f is 2TP. And so the trace of f is TP, although I'm being slightly loose with my language here. And so you get, well, if the trace of Frobenius is TP, then TP must be this coefficient here, and you're done. Okay. So last thing, I know this is a lot of kind of seemingly disjoint facts, but the thing that ties them all together is they're all about Hecke algebras over various rings. Okay. You can also show that TZL is free of finite rank over ZL. And so then standard commutative algebra shows that TZL has to decompose into the product over T sub m's, where the product runs over all maximal ideals M of T sub ZL. This is just a generic fact from algebra about modules that are free of finite rank over, say, ZL in this case. Okay. And TM here is the localization of TZL at M. So take TZL, localize at the maximal ideal M, take all possible localizations like that and take their product. That product must just be the ring itself. Okay. And TM is a complete local Z algebra. That's not hard to check at all. It's also free of finite rank as a ZL module. This is all basic commutative algebra stuff, but we'll pull on this once or twice later. Okay. You can see chapter 10 of my notes coming up quite a ways from now, since we're still in chapter 3 of my notes, but we're almost done with chapter 3. So next time we'll take all this information we've learned over the past several videos, and we will revisit and conclude our discussion about conjecture 1. So thanks for watching, and I'll see you then.